Everybody, this is Mrs. Ellsworth. What we're going to be talking about today mostly is the scientific method, but actually the claims, evidence, and reasoning in this portion of Chapter 2. So let's go ahead and get to it. In the old-fashioned scientific method, you would make an observation, you'd see something happening, and so you'd ask some questions, and from these ideas you could form a hypothesis. This is something that you think will answer the question, and that will be a way for you to test it, so that you can gather some evidence, come up with some ideas to support them with your conclusion. If it doesn't support it, then you go back to the drawing board and start again. Or else you go ahead and communicate results in a report or in a presentation. But we're not going to go through all those steps. We're going to simplify it a little bit, and we're going to do our claim, evidence, and reasoning. So that is what we've been talking about for a couple of years now in our science here at Parker's, and so now we're going to continue doing that. But let's go and make a comparison between this and the old-fashioned scientific method. The old-fashioned scientific method, you would look at these two portions of it about making that observation and coming up with a question, and that would really be our guiding question. Quite often for us, we come up with a guiding question from some phenomena, and then we are able to make a question so that we can test it, see what's happening. Quite often we will form a claim right away, which is our hypothesis in the old-fashioned one, and this is something that must be testable. And it's going to answer a question also. So the claim and the hypothesis are really quite a bit alike, but there's a little bit of difference, and I'll talk about that here in just a moment. Anyway, so then looking at the next section, testing your hypothesis, analyzing those results, coming up with graphs or whatever. Anyways, this is what we would call our evidence in our evidence portion of our reports. Okay, and then the whole last bottom part, okay, so we got a claim, evidence, and now we're going to explain our evidence. Okay, we're going to explain our evidence, and that's going to be our reasoning. Now, I just want to point out that what if your evidence doesn't support it? What do? You go back and you figure it out, and you come up with a new claim. So it isn't over if it refutes the whole idea of this claim. Those things are important too, but do you have to go back and reinvestigate it? Because it's highly likely. Okay, so I was just noticing as we were eating hamburgers that, and I'm just going to do a claim, evidence, reasoning here. I was just noticing when I eat hamburgers, I like the ones with the cooked onions on them. They're nice and sweet. And these ones down here, these raw onions, they are starchy. And so that doesn't throw me so much. So I was wondering, well, why do cooked onions taste sweeter than raw onions? And that's a valid question. Anyways, but it's not a guiding question. It's not guiding us anywhere. It's just telling us sweet onions, raw onions, what's up? Okay, and so you go and do a little bit of investigation. You find out that there's starch in raw onions, and then the cooked ones, obviously they taste sweet. So should there be some sugar in those ones? So you can go ahead and make a claim from that. Okay, and my claim. Okay, so here's what I'm thinking. I will test both raw and cooked onions for the presence of sugar and the presence of starch. If the raw onions have starch and no sugar, and the cooked onions have sugar and no starch, this will support my claim or my hypothesis, my claim, that the starch in raw onions chemically change into sugar, when we're cooking it or heating it. Okay, so that's my claim there, this bottom portion of it. And I left the word hypothesis there for a moment because you might be somebody who also looks into that information, and they still do some of that with research in college. So it doesn't hurt to be familiar with some of those older terms that we are kind of slipping away from in high school. Okay, we claim that the starch in raw onions chemically changes into sugar when heated. Okay, so we're going to, remember we talked about all this testing. We're going to cook raw and cooked for both starch and sugar. Okay, and you have to test both, because if you do find that raw is starch, positive for this one, and cooked is positive for that one, you do find that you'll, it doesn't really prove it if the, you got to check to see if there is no sugar here. Well, we went and tested it, okay, and we got this for a result. Surprise, surprise. So this isn't supporting anything in our claim. Okay, our claim, we claim that starch is in raw onions, chemically changes into sugar when it's heated. That's not true. There's sugar in both, there's starch in both. So no, this does not prove our claim. It doesn't support it at all. Okay, and so you'd have to go back to the drawing board and figure out something else there. What makes that so that sugar is more expressed and easily to taste in the cooked onions versus the raw onions? And there is some things that mute it, and I can't remember all the details on that, but I have read this investigation, but no, it is definitely still starch and sugar in both of them. But for some reason, you're able to taste one more than the other one. And it's because the raw ones have so much other flavors in there that you're not really detecting the sugar so well. But in scientific investigations, how is that hypothesis similar to a claim? Well, let's go and read what a hypothesis is. Okay, it's a possible answer to a question. Okay, a possible answer to a question. It must be testable, and you also should state a little bit of your method in it. Okay, testing both raw and cooked onions. Okay, and then I went and looked up some information, and this AI answer was pretty good here. The scientific claim is similar to hypothesis because both the statements propose a potential explanation or outcome on your evidence. Both should be testable and falsifiable, so it could be refuted or supported, okay? But here in the bold, essentially a scientific claim is a hypothesis that is backed up by experimental data and is presented as a conclusion based on a research finding. So a claim has been done. A hypothesis is going to be done, okay? And so a claim is actually taken that hypothesis and you already found evidence for it, and you're able to make that claim. Okay? Okay, so does a hypothesis graduate into a theory? No. And does a theory graduate into law? No. So lots of times students say, well, think that one graduates into the next after more data. No, it doesn't. Okay, they're totally different things. But what we're going to have to remember here is, what is a theory? Okay, and so a theory is a broad generalization that explains a body of facts and phenomena. We are not able to prove them. Okay, a theory just exists. We've got evidence for it, but we're not able to prove them. And I'll explain that here in just a moment. Okay, what is a law? A law is a natural law or law, okay, is an explanation of how something occurs. So a theory probably explains more of why it occurs the way it does. This one explains how it occurs every time. Every time it'll be, and we're able to gather so much evidence on this one too, over and over and over, okay? And it's completely supported. So they are two different things, but this right here has evidence to prove it. This right here does not, and I'll explain that. Okay, so hypothesis can be like a claim too, with those if-then statements to begin your data collection. But like I said, a claim is probably after you have picked this hypothesis in your head and you've chosen a claim to make, and you have the evidence already for your claim. Okay, and so with the theories, you can have all kinds of theories, like the Big Bang. We can't prove it. No, we can't. So it won't ever be a law. Okay, because a theory you can prove over and over. We will never be able to prove this, but we've got scientific evidence showing how the universe is expanding, and all that other evidence showing how that the elements created from hydrogen with them melding together and all those type of things. We've got tons of evidence of that. Okay, and like this one right here too. What's this one? Plate tectonics. Okay, there is all kinds of evidence of this too, but it is still a theory. Okay, the atomic theory. They keep on tweaking this one. It keeps on changing it. Keeps on getting a little more deeper and deeper and deeper into more information about it. But they have not proved it, and they will never be able to see an atom either. Because think about it, like even the electron tunneling microscope, it is made up of a single atom at the bottom. How can you have an atom? You see what I'm talking about? The size just won't ever work there. You need something smaller than an atom, and that doesn't exist. You've got pieces of atom, but they're still not something that is... I'll just get off of that soap can. Anyways, so I guess it's a soapbox. Anyway, here's a law, okay? Good law of gravity. Anyway, so every single time that objects are pulled towards gravity. Okay? So let's talk about independent and dependent variables. Okay? Here's some easier definitions of them. An independent variable is the change variable. That's the one that we want to change. So like in our onions experiment, Okay, that right there, we changed the cooked onions from the raw onions. That's the only thing we changed. Okay, those are the things that we were changing. The dependent variable, oh goodness, this went crazy here. Okay, this right here, this arrow should be going to dependent variable. Anyways, the dependent variable is the one that you measure. So this right here is always your outcome that you're looking for, the certain types of results that you're looking for. And quite often, these right here will be your measurements. Okay, well, there's a way of putting these onto a graph too. Okay, so if you're looking for something for your independent variable, okay, that is always out on your x-axis, and the one that you measure or your dependent variable is the one that you get your results for. So if you're talking about a simple one of distance and time, seeing something move through time, your time would be here on the bottom. Time is always on the bottom, by the way. And then your distance would be up this way. And so just to let you know that will help prove several things there, and it makes your data so much more understandable when you put it in this order too. Otherwise, sometimes it can be backwards. Instead of being increasing, or it'll be decreasing or whatever. Okay, so when experimenting, we need to think about constants and controls, and we're going to talk about this more in class. But the whole thing is that you need to be able to have your constants and your controls. They don't equal the same thing. A control is one thing that you're looking for that you should get the same results every time. Okay, so here we go. We got, does hot water freeze faster than cold water? Mr. Paul Pops Ickles decides to conduct an experiment. He decides to put 2 ice cube trays in the freezer, one filled with cold water and the other filled with hot water. Pops will check the trays for ice periodically. What is the dependent variable and the independent variable? Okay, so what is the one that he's changing? That's your independent variable. It would be the 2 different temperatures of water. What is your dependent variable? That's the one you measure. So he's checking to see the time that it takes for one to freeze first, right? Okay, so then you need to keep a whole bunch of things the same. But these are called constants. You need the same freezer. You need the same size ice cube trays. You need the same amount of water in them. What other things can you think of that should be identical too? You need to make sure that you get your water from the same area. Maybe you want to do them with both distilled water so that one doesn't have some sort of minerals in it that the other one doesn't. Okay, so what other ones could you find of these variables? These are the constant variables that you could think of in this case to make it a valid test. Okay, there is one that you could also do too that would be a control. Now you'd have to have one of these 2 picked as your control. Okay, because if they both don't freeze, then there's a problem. Okay, and you know it's your control, you want it to freeze. And it's usually the one that you're comparing to, or else it's one that's set off to the side. So I'm going to ask you to do that with a different one, and then tell me what you know about it when we return to class. So here we go. 11 of the students at the high school became ill after an hour after they ate the school lunch. One thing that they all had in common was eating the school lunch. Mrs. P. Uke at the school head cook claimed that each food item on the menu was fresh. The menu consisted of a hamburger made of soy, pickles, ketchup, peas, and carrots, apple crisp, and milk. Okay, so if you're going to do an investigation on this, what would be your independent variable, your dependent variable, and your experimental control? Okay, so come up with some ideas for those, and we will have to talk about those in class. I will see you then. Bye-bye.